Welcome to the beach. Today we're going to be talking about coastal erosion. And this is a typical coastline, a real pretty one up on Cape Breton Island in Nova Scotia. And we're going to see how beaches and coastlines like this work. Now, understanding coastal erosion and the processes that affect coastlines is really important because when we look at it, 30 of the 50 states have coastlines, right? They're up against a major body of water. And so this can be the Pacific Ocean, the Atlantic Ocean, the Gulf of Mexico, the Great Lakes, any of those are major coastlines. And 85% of the U.S. population lives in those states. So a large portion of Americans live somewhere where they should at least be thinking about coastal erosion and how coastlines work. Now, when we look at coastlines, we can first of all look at things tectonically. So we're going to begin with a passive margin. A passive margin is not a plate boundary. So it's going to be like the east coast of the United States or South America. Often these are going to have wide and sandy beaches, and they might have offshore islands, and they're going to have a wide continental shelf. So that's very much like what we have down here in Texas, right? On this map, this blue area right there next to the continent, that's the continental shelf. That's an area of water that's relatively shallow. It's 200 meters deep or less. And so we have this wide continental shelf here. And we do have those offshore sandy islands. That's basically like your barrier islands of Galveston or South and North Padre or Matagorda Island. That's our passive margins. Now, we could also have an active margin. And an active margin is a plate boundary. So that would be like the west coast of South America. And at these active margins, you're going to have a lot of earthquake and volcanic activity. Notice you don't have as much of a continental shelf there. It's going to be very, very thin. And oftentimes these have cliffs above the beaches. Now, can you have sandy beaches in an active margin? Sure. Can you have cliffs at a passive margin? Sure. But this is just kind of what's typical of each of these. Now, when you go to the beach, kind of what sort of things would you expect to see at the beach? The anatomy, the parts of a beach. The beach is the gently sloping area where the waves wash back and forth. It doesn't have to be sand. We usually think of beaches as being sand, but they can be any kind of sediment, really. Now, the beach face is the area subjected to wave action. So this means waves are going to be hitting it, maybe eroding it, maybe depositing sediment, but it's subjected to some kind of wave action. Then there's an area called the berm. The berm is a flat zone landward from the beach, and this is created by the waves depositing sediment. So that's what we're seeing right here. Right here, that's going to be the beach face where the waves are acting on it. And see this flat area? That's a berm. Sometimes you'll have multiple berms related to normal waves versus storm waves, which are typically higher. In fact, here, this is following a storm where waves had been higher. And you can see those waves actually covered this berm at this area. Now, waves, which are one of the big things that shape our coastal areas, have some parts to it as well. So on your typical wave, you have a crest, which is the high point. You have a trough, which is the lowest point. You have the wave length, which gets measured from crest to crest, or you can do it from trough to trough. You just have to be consistent. You have the wave height measured from the trough to the crest. That's our wave height. Then there's something called wave base. Well, to understand wave base, we have to take a look at how water moves in a wave. Water does not move in a straight line. In a wave, water moves in an orbital motion. This kind of circular motion. That's why if you throw something in the water, you'll watch it kind of rise and fall and bob up and down because it's undergoing this circular orbital motion. Well, as you get deeper, that motion gets less and less and less until you reach a point where there's no more circular wave motion, and that is called wave base. And wave base is equal to half of wavelength. So if your wavelength is like 10 feet, well, your wave base is going to be 5 feet. So below that, there will be no movement of the water because of the waves. Now, waves can have different characteristics. You can have long waves, they can travel fast, they can travel slow, sometimes they're higher, sometimes they're lower. Well, all of these characteristics of the waves are controlled by the wind, because your typical ocean waves are created by wind. So the wind speed is going to be important. The faster, the stronger the wind is blowing, the bigger the waves are going to be. But the wind duration is important as well. If you get one gust of wind at 70 miles an hour, that's not really going to make big waves. But if you have several hours of 70-mile-an-hour winds, now you're going to start getting some very big waves developing. So the duration is important as well of the wind. And then there's something called fetch. Fetch is the distance the wind travels over water. The farther the wind travels over water, the bigger the waves are going to get. Now, waves do change characteristic as they come on shore. As the waves approach the shoreline, they feel bottom. And what feeling bottom means is wave base encounters the bottom of the ocean. And this is going to slow down the wave. And as the wave slows down, its height starts to increase. And so if you ever go to the ocean and you watch the waves come in, you're going to see this point where the waves start rising higher and then curling over into what are called breakers. At that point, you know wave base is encountering the bottom of the ocean there. So that's what we're trying to show here. There's our orbital motion, right? And these waves come in, but right about here, wave base encounters the bottom, so the wave is feeling bottom. So the waves grow and then form breakers that then wash onto the beach. When these waves hit the beach or the rocks of a cliff at the edge of the ocean or whatever, they can cause erosion. And waves can do this in two basic ways. We have what's called hydraulic impact, and that's simply the force of the water hitting something. And it might not seem like water could break stuff apart, but again, remember, water has mass. A gallon of water is over 8 pounds. A wave's going to be many, many gallons of water. So that's a big amount of weight that's suddenly slamming into something. That can cause erosion. That's hydraulic impact. But that wave is not entirely made of water. That wave might be carrying little bits of sand or some pieces of driftwood or some kind of debris. And that is going to slam into the rock or the coastline as well, and it's going to kind of scrape against the coastline. And that is abrasion. So as these waves hit, they can erode from hydraulic impact and from abrasion. When you are at a coastal area, most coastal areas are going to be affected by tides. Now, all the oceans are affected by tides. The Great Lakes are not. And, I mean, that's a mild lie. The Great Lakes have, like, tides that are this big. So, not very big. So, we don't worry about tides in the Great Lakes, but we do in the oceans. What the tides are, this is the periodic rise and fall of the water level in the ocean as a result of the moon and sun's gravitational attraction. So basically, we have Earth and we have the moon over here, and what happens is the gravitational attraction of the moon pulls the water towards it. So we're going to get high tide at that location. The sun also exerts gravity because the sun is a very large, massive object, and so that's also going to have an influence in tides. In fact, we have different names for tides. There's the spring tide. The spring tide is when we have the greatest tidal extreme, meaning the biggest difference between water level at high tide and low tide. And this occurs because the sun, the moon, and the earth are all in a line with each other. So the moon and sun are helping pull the water towards themselves. Neap tide is the opposite. This is the minimum fluctuation between high and low tide. And this is because the moon and the sun are at a right angle to each other, so they're kind of battling each other. They're pulling the water in different directions. So basically, here's our spring tide. We have the earth, the moon, and the sun all lined up, so working together to create that tide. And in this case, we have the sun over here, the moon over here. They're each pulling in their own direction, so we don't get as much of a tidal fluctuation. Different areas of the world have different high and low tides. Some places have a big fluctuation between high and low tide, some you don't notice it as much. And this has to do a lot with the shape of the coastline and basically how quickly or how gently the topography along the coastline is. But the place in the world that has the biggest extreme between low tide and high tide is the Bay of Fundy. And this is giving you the highest tides. So the fluctuation between high and low tide can be as much as almost 50 feet in some areas. And so we can see that in this satellite image. This is at high tide. All of this blue is water. And this is at low tide. Notice all of this, which normally is covered with water, is now above water. And there's the Bay of Fundy at high tide, and there it is at low tide. So we can have some very extreme tidal fluctuations depending on what coastline you happen to be at. Sometimes you hear people talk about tidal waves, and this occurs when the tide is rising. And this is a tidal wave at the Bay of Fundy. It doesn't look like much. Again, some places have ones that are much more impressive than this. But most of the time they just look like that. Another place where they have major fluctuations in tides is in northern England. So this is the border between England and Scotland, and we're going to go to this location called Holy Island, which we are looking at right here. Here's Holy Island, and then this is called the Tidal Causeway. It's above water at low tide, but below water at high tide. This is what it looks like. Notice all the water all over the place, and that's because at high tide, that's underwater. There's all kinds of warning signs around there, right? Like, don't drive here when there's water. They even tell you when you should not go driving out there because you're going to get stuck. But every year this happens. Someone gets stuck in the rising tides because they don't read the instructions. Now, why would you go out to Holy Island? Because in Holy Island there is this. This is Lindisfarne. This is an old monastery from basically the 700s AD. And it is famous because it is the place where there was the first recorded Viking attack on England in 793 AD. And you can still go there and see the buildings. And that's why people like to go out there. All right, let's take a look a little bit at some currents that that can be created as waves arrive on the shoreline. And one of these things is called Longshore Current, which creates something called longshore drift. So if we have land over here, hopefully that says land, I'm writing upside down, and we have the ocean out here. And these are going to be the crests of waves arriving at shore. So these wave crests are traveling this way. Well, what happens when they hit the coastline is if there's any sediment here, the wave is going to push the sediment this way as it comes onto the coastline. And then when the wave goes back into the water, it's going to pull that sediment this way. And then the next wave is going to push it that way. And then when it goes back into the water, it's going to pull it this way. So over time, all your sediment is going to get pushed in that direction down the coastline. And so that's really what this longshore current is. You get these waves arriving at the shoreline at an angle, and it creates this longshore drift of pushing the sediment parallel down the coastline. So that's what we're seeing right here. We have these waves arriving at an angle to shore, and so they are pushing the sediment basically towards us. Another current that is created by waves is called a rip current. And a rip current is a very narrow, very fast-flowing current that goes from the coastline into the deeper water. And this occurs where water accumulates along a shoreline. So basically a wave arrives, it starts going back into the ocean, but before all that water can go back into the ocean, the next wave arrives, shoves all of this up against the beach, and eventually enough water kind of gets shoved right up against the beach that it's unstable, and a rip current forms that flows very, very fast out into the deeper water. And these are narrow, so they're easy to escape. If you ever get stuck in one, just swim parallel to shore, and you're going to be out of the rip current very, very quickly. This does erode sediment from beaches because it can pick up some of the sand from the beach and take it out into the deeper oceans. How can you tell if there's a rip current somewhere? Notice right here we have this wave, and it looks like the wave crest is disrupted right there. Well, it's disrupted because there is a rip current flowing in the opposite direction. It's going into the deeper water as this wave is arriving. Now these currents that are created by the waves, and the waves themselves, can cause a significant amount of erosion. And this is something that affects many people who live in coastal areas. And most of this cliff erosion occurs during storm events. And that's because normally cliffs look like this. That water is not doing a whole lot of eroding on this day, right? But when we have a storm event, we're going to have big waves crashing against the base of that cliff. And so that wave action, right, remember the hydraulic impact and abrasion, that's going to hit the base of the cliff and it's going to undercut it. It's going to erode away a notch there, and then there's no support, right? Remember from mass wasting, undercutting, gravity can take over and make these rocks fall. And in fact, that's exactly what happened to these rocks here. They were somewhere up here on the cliff. There is nothing supporting them, so gravity could take over and make those fall. Same thing that we see here. This is at one of the Great Lakes. And I've said it before, the Great Lakes act very, very much like oceans. As waves arrive at shore, they can get bent. This is called wave refraction. You see how this wave is not in a straight line? It's actually curved right there. When these waves get bent by this wave refraction, this can concentrate which areas of the coastline get the most erosion. So here we have those curved, refracted waves, right? That's what these lines are. That's the wave crests. And these arrows show you the energy of the wave arriving at shore. And if you notice, most of the wave energy converges on these areas we call headlands. In bays, you tend to get lower energy, which is why you often get sediment accumulating in those areas. So we have this nice wide sandy beach in this bay, and our erosion is focused right there. And so this, like I said, this erosion can be concentrated on these uneven coastlines. And we're just going to finish looking at cliff erosion by taking a look at a classic location in Britain. This is in Dunwich, England. This was 1785. There's the same church in 1903. There it is 2 years later. Notice part of it fell into the ocean. There's the ocean right there. Here's the cliffs. There's the ocean, there's the church. That's 1912. And then in 1920, that's all that was left in that cliff erosion.